Let's delve deeper into the chemistry and physics behind the interactions between mercury with aluminum and iron, and why they behave differently. Mercury and aluminum, amalgamation process. Mercury has the ability to dissolve many metals, forming alloys known as amalgams. When mercury comes into contact with aluminum, it penetrates the surface of the aluminum, creating an aluminum-mercury amalgam. This amalgamation process disrupts the structural integrity of the aluminum protective oxide layer. Aluminum is known for its ability to form a thin, protective oxide layer, aluminum oxide, alco, almost instantly when exposed to air. This layer is only a few nanometers thick but serves as an effective barrier against further oxidation and corrosion. Mercury disrupts this protective oxide layer by amalgamating with the aluminum, preventing the oxide layer from reforming. This allows oxygen from the air to reach the fresh aluminum beneath, leading to rapid oxidation. Corrosion mechanism. Once the protective oxide layer is compromised, aluminum reacts with oxygen to form aluminum oxide. This process is exothermic and can be self-sustaining as long as the aluminum surface is exposed. The aluminum continues to oxidize, and since mercury continually prevents the formation of a new protective oxide layer, the process leads to significant corrosion and degradation of the aluminum. Mercury and iron. Lack of amalgamation. Iron does not form an amalgam with mercury under normal conditions. The atomic structure and bonding characteristics of iron do not favor the formation of a mercury-iron amalgam. The interaction between iron atoms and mercury atoms is weak, meaning mercury cannot penetrate and dissolve into the iron surface as it does with aluminum. Oxide layer in iron. Iron forms a different kind of protective oxide layer when exposed to air and moisture. The iron oxide FeO, commonly known as rust, forms a flaky and porous layer. While this rust layer is not as protective as the aluminum oxide layer, it does offer some resistance to further corrosion. The rust layer is not easily disrupted by mercury. Therefore, the underlying iron remains largely unaffected by the presence of mercury. Chemical reactivity. Iron's chemical reactivity with mercury is much lower compared to aluminum. The interaction between mercury and iron atoms is not strong enough to cause significant disruption or corrosion of the iron. Additionally, iron has a different electrochemical potential compared to aluminum, making it less susceptible to the corrosive effects of mercury. Practical implications. Industrial safety. In industrial settings where mercury is used, it is crucial to avoid contact with aluminum components. Mercury spills on aluminum surfaces can lead to rapid degradation and failure of aluminum structures. Iron and steel equipment, on the other hand, can safely come into contact with mercury without significant risk of rapid corrosion. Environmental considerations. The amalgamation of mercury with aluminum can release toxic aluminum compounds into the environment. This poses environmental and health risks, necessitating careful handling and disposal of mercury and mercury-contaminated materials. Scientific and educational use. Understanding the interaction between mercury and different metals is important in scientific research and education. Demonstrations of mercury's effect on aluminum can illustrate concepts of chemical reactivity, oxidation, and corrosion. Conclusion. The fundamental difference in the behavior of mercury with aluminum and iron lies in the ability of mercury to form amalgams and the nature of the protective oxide layers formed by these metals. Aluminum's protective oxide layer is easily disrupted by mercury, leading to rapid corrosion, while iron's rust layer and lower chemical reactivity with mercury prevent significant interaction. This understanding is essential for handling these materials safely in various applications.